So last time, as far as I remember, all you were here last time. So you may remember that last time I introduced linking diagrams and actually proved a certain theorem about them, purely geometric theorem, absolutely elementary, that if you have, well, the statement may be not elementary, but I mean this, that if you have, say, a simple complex Lie algebra, and the system of roots, set of roots, then there I introduce in more or less arbitrary way the notions of positive and negative roots, just cut the space H star into two pieces, call them positive and negative, and there are positive roots, negative roots, and simple positive roots are roots, positive roots which are not sums of other positive roots. Then the system of simple positive roots, the number of them is equal to the dimension of H, which is also called the rank of G, the rank of our Lie algebra. The system of positive roots with their length and angles. Everything is given up to extra similarity. The system of vectors satisfies some simple geometric properties. And these properties are so strong that actually we can list all the possibilities for this system. They are presented traditionally by the so-called linking diagrams. And on this board I made drawings of all possible linking diagrams. So please say to me what I need to repeat of that. Well, frankly, it is not necessary that you precisely remember it, because today I'm going to say something related to Lie algebras. With this classification of system of simple positive roots. By the way, I want to make one very obvious statement, obvious remark. So the following: what we classified, I called this admissible system of vectors. You remember, and it is very clear that if we take an admissible system of vectors, just multiply all the vectors by some number, like 2 or square root of 3. That will be another admissible system of vectors. So admissible system of vectors admit this multiplication by numbers. Unlike the system of roots, because roots, you know, they satisfy, if you prefer that I write it more specifically, say it more specifically, they satisfy a certain relation. This, I mean this. Hop, version 1. I mean this. The input of two roots is equal to the sum over all roots there is such a relation, which shows that we have no right to multiply roots by numbers, because the degrees are different. Definitely right, and on the right side. Well, still what we have a classification of all system of simple positive roots linking diagrams. And my first remark is that if two simple Lie algebras, if you wish, have the same linking diagrams, that is, the same systems of simple positive roots, I mean same systems in the sense that we know the angles between the roots and the ratio of the lengths, then they have the same system of roots. So simple positive roots are just small amount of roots. But they determine everything. Why? If you have two the algebras, so to the same dimension because the number of simple positive roots, the same dimension of h at least, yes, of h. And they have the same in pure geometric sense, systems of simple positive roots. Then I want to say that they have that all the roots are the same for them. Just look. There are other roots, here and here. And we count, say, in the positive direction from the plane, and we find the first occurrence of such a thing, that we have some root here, which is not a root here. First time. So before that, everything was okay. But this time it's not okay. So what to do? Look at this thing. If this root is simple, then this root belongs to this system. Then it is also here because the simple system of simple positive is the same. Not simple. What does it mean? It means that it is the sum of two different positive roots. Right? These roots should be here also. Because before this, to the left of this, the systems are the same. Now, so if this is, say, alpha, this is beta, this is alpha plus beta, this is called alpha prime, beta prime. You see, this alpha plus beta belongs to a series of roots. And the size of this series is fully controlled by the inner product between alpha, beta, alpha, beta, beta, and alpha, beta. Remember, such numbers, P alpha, beta, Q alpha, beta, they are the same for this. So if this is a root, then this also should be a root because the series have the same size on the left-hand side and right-hand side. You remember, there are two numbers, P alpha, beta, and P beta alpha, and Q beta alpha. And they are fully determined by inner products. And this is all. So all positive roots are the same for the two Lie algebras, and hence all negative roots are the same because they are just minus positive roots. And that's all. Now we should resolve a very radical equation. If we have two Lie algebras, well, of the same dimension, I mean two simple complex Lie algebras of very much the same dimension. And we have some linear isomorphism between, for both we have Cartan subalgebras. We have some linear isomorphism between these Cartan subalgebras, which take roots into roots. You understand? Then, what we want to prove? The algebras are isomorphic. As soon as we do it, then our classification of Dynkin diagrams becomes, well, with some reservation, becomes a classification of simple Lie algebras. Why is there reservation? Obvious. We have Dynkin diagrams, but we so far do not know, have no proof of the fact that every Dynkin diagram does correspond to some Lie algebra. But at least if at least our classification of Dynkin diagrams, as soon as I prove that the theorem which I formulated, this classification of Dynkin diagrams is at least contains the classification of simple Lie algebras as this part. Maybe some of them, well, actually it doesn't happen. But at the moment we don't know. Maybe some Dynkin diagrams do not correspond to any Lie algebra. By the way, this equation, when Cartan created all the theory which I present this now, For some Dynkin diagrams, Lie algebras were not known. They were found later, and the latest was certainly E8. But this is another question which we will discuss. But now, this theorem I have formulated, if I haven't formulated it so far, that if we have a linear isomorphism between two Cartan algebras of two simple Lie algebras, and this isomorphism takes roots into roots, Well, roots are elements of the dual space. We have actually an isomorphism. You can say the dual isomorphism takes roots into roots. Then these two Lie algebras are isomorphic. Moreover, this isomorphism between Cartan subalgebras can be extended to an isomorphism between Lie algebras. This is the theorem which I want to prove now. Questions? Henry.
So eventually we'll be able to translate these different maps into maps of the Dynkin diagrams. We'll be able to see the different automorphisms of the Cartan from the Dynkin diagrams.
I want to translate the question into something which I understand. Some Dynkin diagrams have symmetries. So it is possible to map a Dynkin diagram into itself by, yes. Then there is automorphism of the corresponding Lie algebra. Moreover, if you have not an, well, I wanted to formulate it later, but you forced me to do it now. If you have not an isomorphism, but just a linear map between two Cartan subalgebras of very much different dimensions, maybe. And then we have the dual map between the dual spaces. And suppose that this map takes roots into roots. Then this map between Cartan subalgebras is extended to a homomorphism between Lie algebras. It's also true. It's also true. Actually, this statement, so if you have a part of a Dynkin diagram, maybe even disconnected, then yes, the big Lie algebra contains the small Lie algebra. It may be actually not simple, semi-simple if it is disconnected. Everything is this. Well, but I will begin with a theorem, and actually, if I formulate further theorems, I will improve them anyhow. They will be in my notes as exercises. I know two exercises which I'm going to. Actually, this morning, maybe an hour ago, or something like this, I mailed a new version of my notes. This new version contains my previous lecture, but not my lecture today. I will try to write it also. So theorem, we have two Lie algebras, two simple complex Lie algebras, G and G prime, two Cartan subalgebras, H and H prime. This map, which I suppose to be an isomorphism, which precisely establishes correspondence between systems of roots. So the dual spaces also are isomorphic, and for every root alpha here, we have a root alpha prime here with everything, I mean with all inner products also corresponding to each other. By the way, it follows from this that this map between H and H star is an isometry. If it preserves in the products of so many vectors which form a basis, then it has we have no choice. So this becomes an isometry. It preserves in the product. Yes, so we have this. And from this, I want to deduce an isomorphism between G and G prime, and by definition, it will just extend this isomorphism. Have doubts, Henry? It looks like this. Good. Alpha and alpha prime, and I will usually denote by we use prime notations for everything related to G prime and H prime. Suppose we have two roots, alpha and beta. Then alpha plus beta may be a root, maybe not a root. If alpha, first of all, even before two roots, one root. So I have G alpha, right? In this G alpha, I choose an element E alpha. This is one dimensional, so non-zero vectors. And the only thing which I prefer to have is that E alpha, E negative alpha, this direction, this. Yes, in this order. This minus is actually my tribute to tradition. Right, plus in the theory will not be any worse. So E alpha in every G alpha with this only condition. This in the product is H alpha times the number, but I choose E alpha and negative alpha in such a way that it is my minus H alpha, okay? Then what is E alpha? E beta. It is 0 if alpha plus beta is not a root. But if alpha plus beta is a root, then it is E alpha beta times some number. And this number is very much traditional. It's denoted as capital N alpha beta. I do not choose this notation, it's traditional. These numbers, N alpha beta, obviously fully determine the Lie algebra, because the Lie algebra is spanned by H, where the commutator is zero. So we know everything now about the commutators of some of H and this E alphas. So the commutator is fully determined by this, okay? Now, these numbers, yes, and so what we want to set up a basis in G prime with the same numbers. But this is in the future. First, I want to say something about these numbers. There are some relations between them. Some of them are obvious, some of them are less obvious. 4 relations. First, N alpha beta is equal to minus N beta alpha. Second, I got 3 roots, and alpha plus beta plus gamma is 0. I prefer to say that, well, non-zero roots. It's all I need. Then the following is true. I didn't say that if alpha plus beta, it is not for this. In this case, alpha beta is a root, negative gamma. But if alpha plus beta is not a root, then I simply set N alpha beta to be 0. Not obliging in this case. So in this case, N alpha beta is equal to N beta gamma is equal to N gamma alpha. Statement number 2. Statement number 3. Suppose that we have a better relation. Then the following is true. N alpha beta times N gamma delta. And then cyclic permutations with respect to alpha, beta, and gamma. So N beta gamma N alpha delta, N gamma alpha, and beta delta is 0. And the relation number 4 is the following. N alpha, so we have two roots, alpha and beta, and alpha and beta. And we suppose that beta is not plus minus alpha. That's all. So three roots which are not collinear. Then alpha and beta is not plus minus alpha, and this implies that n alpha beta times n minus alpha minus beta is equal to minus minus appears later 1/2 alpha alpha, and here I should write q times 1 minus p. You remember that for every two roots there are numbers p beta alpha and q beta alpha, which measure the size of the series roots. Beta plus k alpha is a root when k is between this p and q. P is non-positive, q is non-negative. And so I write this. And this p and q are this p and q. These are the four relations. This is the definition of n alpha beta, and I suppose that you remember it because I am going to erase it. So n alpha beta is this coefficient. Very interesting. Number 1 is obvious. So obvious that I even don't want to waste a line for it. My board is not this big. So n alpha beta and beta alpha is the same, only with the sign minus. So the first is obvious. Number 2. Certainly to prove both 2 and 3, we need to use Jacobi identity. So number 2. Write E alpha, E beta, E gamma. Then I will use the Jacobi identity. But first let me compute this. So this is E alpha beta, E alpha, and beta gamma, E beta plus gamma. And E beta plus gamma is negative alpha. And so this is now n yes, so this is just E negative alpha. E alpha negative alpha is H alpha, right? So this becomes n beta gamma H alpha.
Is it negative though?
Negative alpha. Alpha plus gamma is 0.
Oh, E alpha with E negative alpha. Isn't that negative alpha?
Ah, yes, this minus actually.
Traditional.
No, it doesn't anything good. I sometimes erase. Thank you, Colin. I didn't prepare this lecture, so you understand my difficulty. Yes. Now, if you do the same for the three double commutators obtained from this bicyclic permutation, then you get the following: negative n beta gamma H alpha minus it is 0, right? But you see, alpha plus gamma is 0. And particular H alpha plus H beta plus H gamma is 0. H alpha, H beta, and H gamma are not collinear. They may belong to the same plane because their sum is 0, but not to the same line. So any two linear relations between them are proportional. Here the coefficients are 1, 1, and 1, right? So from this it follows that, yes, n beta gamma, n gamma alpha, and n alpha beta are all the same. No questions? Number 3. Well, again I use the Jacobi identity, but now I have 4 roots, so I prefer to write again E alpha, E beta, E gamma, and I do the same, but now it is not negative alpha anymore, it's beta plus gamma. So I will get the following. It is n beta gamma, then n alpha beta plus gamma, and it is E, the sum of these 3, right? Negative delta, negative delta. Right? Now, about this. This is negative alpha minus alpha minus delta, right? The sum of 3 things, this, and this, is 0. Right? So we can apply our previous statement to this n. And we get that n alpha beta plus gamma is equal. So what we do? We take this and this, and we can replace it by this and this, right? Delta alpha. Delta alpha, and I prefer to write minus alpha delta. So this follows from 2. Look at this and agree or disagree. So this n alpha comma minus alpha minus delta, according to these 3 things, alpha minus delta, and delta, have 0 sum. So we're going to apply the previous statement. And the previous statement says that in this triple, alpha minus beta, and delta, we can make cyclic permutations. One of them makes this alpha beta plus gamma, it makes it into delta alpha. And since I prefer to keep this alphabetic, I write minus alpha delta, using, if you wish, the relation 1. Okay? This is all. Yes, I will keep these 2 relations, but here this I can erase. And you see that E alpha, E beta, E gamma together. This is n beta gamma, n alpha delta, E negative delta, right? E negative delta anyhow is not 0. Then the 2 more equalities which are obtained by a cyclic permutation of alpha, beta, and gamma. And they will have the 0 is equal to, and the sum of 3 cyclic permutations of this, I mean cyclic permutations of beta, gamma, and alpha only. Delta doesn't participate in this permutation. Plus n gamma alpha and beta delta plus n alpha beta and gamma delta, and this is 0. This was number 2. Number what? Number 3. Number 4 is less interesting. Although it is very important. I will not make actually, I will not observe all our formulas, but you can believe that we already have a formula for this. Why so? This is because actually alpha, negative alpha, and beta. I say alpha, negative alpha and alpha plus beta. They belong to a certain series of roots, right? And if so, so there is a formula. I will not derive it precisely from the existing formulas, but this is equal to this. Q minus, now it's important that there is a minus. Q, 1 minus P, and E beta. Yes, so we take commutators of E beta first with alpha, then with E negative alpha. We are back in G beta now, right? And we know we know enough about the commutators to derive this. So when we commute E beta first with E alpha and then with E negative alpha, we are within the series of roots beta plus K alpha. And within this series, we know all the commutators. So this formula, let me assume that this is known. But if so, then we immediately get this relation, because this is what? N alpha beta, N minus alpha plus beta, right? First, I commute this is E alpha plus beta with this coefficient. Then this, and this is equal to this. But regarding this, we'll also have something, because negative alpha plus beta, and negative beta. This three things again form a system of roots with zero sum. And we can, instead of this, we can take this. So this is equal to n negative beta negative alpha, which is minus n negative alpha negative beta. And as soon as you substitute this instead of this, you minus here, extinguishes the minus there, and we have precisely the relation which we wanted to have. That's all. Let me say a little bit more than I need. A lot more, but I will not say much about this. You see, actually, if we have a Dynkin diagram and don't know the real algebra, then all you need, it is very easy to reconstruct the whole system of roots. And all you need to know is these numbers and alpha beta to construct a Lie algebra. The fact is that if we have, so we have a Dynkin diagram, we have a system of simple positive roots. We have a whole system of roots. And suppose that we are able to find the numbers n alpha beta, which satisfy all these four properties. And it is almost true. No, it is precisely true that these numbers, that we can find these numbers in alpha beta, which satisfy these four identities. And then the commutator, which is defined by these numbers in alpha beta in this space, will satisfy the Jacobi identity. It certainly will be anti-commutative, because an alpha beta is negative and beta alpha. So this is a problem. This problem becomes again a very elementary problem for every Dynkin diagram. The system of roots certainly may be not, positive roots. There are not too many of them. Roots, the number of roots is roughly the square of the number of positive roots. So we have a huge system of roots and a huge system of equations. Not precisely linear, because there is one quadratic equation. And we want to solve them. And as soon as we do that, if we have these numbers, we reconstruct the whole Lie algebra. I can say more. Not only it is possible to do this, it is done in mathematics, but also the result, these numbers n alpha beta, are all integers. By this reason, the field which we have makes no difference now. This can be, if you have a system of roots, this construction can be applied to vector spaces over any field, including for those of you who are interested in that. Fields of finite characteristic, finite fields. So actually, Lie algebras, simple Lie algebras. I don't want to say that over an arbitrary field we have a full classification of simple Lie algebras, but it is the construction. As soon as you have a system of roots for some complex simple Lie algebras, then actually, since certain numbers become integers, not rational numbers, integers. If rational numbers, it's also good. But in this case, we can apply this to a field of characteristic 0. But if we apply this to an arbitrary field, then it also works, because actually these numbers are all integers in this when we solve this problem. And then we have the algebras over finite fields as well. And then using things like, like Baker, Campbell-Hausdorff-Baker formula, we can try to find a Lie group over finite fields, so-called Chevalier groups. This theory is presented in many books. Some people like it. So you can find it somewhere. I will not touch it anymore. I will consider the real case, but in the complex case, this is all. Just to be fair, and why not? I want to make one small remark. Actually, our choice of E alpha and for alphas is a little bit too arbitrary, because all I requested that E alpha commutated with E negative alpha is H alpha. H alpha are here. We have them. But if you multiply E alpha by some number lambda and E negative alpha by lambda inverse, then certainly this condition will still hold. And it is difficult to believe. It's difficult to believe. We can do it for every pair of roots of alpha and negative alpha. It's difficult to believe that we can control the behavior of the numbers in alpha beta, because they can be multiplied by in this way by lambda related to alpha and lambda related to beta. Two complex numbers, why should it be integer? There is one more condition which is usually imposed. I don't need it. That n alpha beta, condition number 5, that n alpha beta is equal to n negative alpha negative beta. This always, so actually when we solve our system of equations, we add one more equation to these equations, this one. And then what I said becomes true. The arising basis in the Lie algebra is called the Weil basis. These numbers are known for all Dynkin diagrams, and they are integers. Questions? If you don't ask anything about this, you will never hear anything from me about this, because it is not. I was not going to touch this subject, but simply I think it is sort of unfair. Now, well, I have 9 more minutes. I hope to say something. So I want to say, you remember what? That actually, if we have 2 layouts of G and G prime, this basis E alpha in G. As I said, there is there remains some freedom in choose of E alpha because we can multiply it by a number. But I want to say that for G prime, I can find the vectors E prime alpha. Well, maybe it's better to say E prime alpha prime, or simply E alpha prime. So you remember, if we have G and G prime, we have alpha and alpha prime, and we have this already fixed. Then we need to find an appropriate system of these vectors in G prime, such that if E alpha E beta is equal to n alpha beta E alpha plus beta, then should be E alpha beta, no, E prime alpha, E alpha prime, E beta prime should be equal to the same n alpha beta, E alpha prime plus beta prime. As soon as I do it, I prove my theorem. Now, if I'm allowed to cheat a little bit, not too much, then I can say that, my friends, it's obvious. Because this condition actually defines everything. You see, it is, yes, n alpha beta. But again, I'm applying induction. Induction. So I have roots. I consider positive roots. I already have something. So suppose that everything is settled up to a certain level. Suppose that alpha prime and beta prime, so all roots are positive. So alpha prime and beta prime are here. And we already have E alpha prime and E beta prime. And then just define E alpha prime plus beta prime by this condition, by this equality. We know n alpha beta, right? And then as soon as we do this, we have this. And this is all. If I am allowed to cheat a little bit, but actually not a little bit. What do you think about this? So I don't need any equalities. I don't need anything. This induction gives me, well, for the beginning, it is all okay. I have just 5 minutes, so I prefer not to say this, but believe me, the real trouble does not belong to this, to the beginning. Everything goes like this. But still there is one thing which requires a work. Do you see it? So you prefer to this is the root alpha plus beta, alpha prime plus beta prime, for which you don't have alpha plus beta so far. But what if alpha plus beta is equal to some gamma plus delta? You understand? So we have a very different gamma prime and delta prime with the same sum. And in this case, we have this E gamma prime, E delta prime, okay? And I write gamma delta, E gamma prime plus delta prime, but this is the same. Right? So my construction fails at this moment. Agree? I don't know which one to take. They give me different E gamma prime, different E's for the same value. So if I denote this as a row, I have two different E rows, E row prime from one hand. What to do? Obvious. You see, if really we have this equality, then we have alpha plus beta plus minus gamma plus minus delta is 0, right? So these numbers, n alpha, beta, and gamma, delta, are not precisely unrelated. There is a relation which have both n alpha, beta, and gamma, delta. This relation is the sum of three things equal to 0. And then actually, I just take here. That's good. And this relation actually shows that if we know n alpha beta, and by some mysterious reasons know everything here, then we know n gamma delta, which certainly can be applied to this, and then everything becomes okay. You see, if alpha, if we have this equality, then it is possible to assume that for these two, actually, I mean, and alpha, so I can assume that gamma is the biggest of them. So for this and this, we already have everything. This is how we should proceed. I cannot say more now, but using this last equality, we can easily conclude that actually these two definitions for E rho prime, the rho is alpha plus beta and also beta gamma plus delta, give the same result. So this is how we use this equality. Number 3, certainly the transition from positive roots to negative roots is not a big deal, because we also have the condition for the equation 4, which precisely relates them. So if we know n alpha beta for G prime, then we also know n negative alpha, negative beta. And this all. Actually, in this computation, we will also use the properties 1 and 2, which are also necessary. But actually, these properties 1 and 2 both were used in the proof of identity 3, so they we do not waste our time when we prove them. So this is how we do it. I will do it next time, precisely the end of the lecture today. But the result is clear. As soon as I resolve this small thing, I will prove that actually simple Lie algebra is fully determined by Upton isomorphism by its Dynkin diagram. Thank you.